Hello everyone, this is Professor Jimenez and I'm going to explain to you the code for lab practice number 1. And here we have this practice where we are reading and writing ports using the PIC 16F 1619. So this first practice we already did it using assembler code. Now we're gonna use it with the PVP3 compiler. And notice that right here we will use in this graph, we can see here that we will use port C, and port B will be the input port with 4 switches, as you can see here on the left side, and port C is where we will be transferring this data. This nibble or the same 4 bits here will be transferred here. But notice that these bits are in the on port B where RB0 to RB3 do not exist. So these locations are using we can see the most significant bits from port B. And we will have to shift these positions 4 times to transfer this to RC0, 1, 2, and 3. Of course, we might need to transfer RB4 through RB7 and put them into RC4 through RC7. That's another option, and there's another way to do it. So right here we have this LED bar graph representing 4 LEDs, which you can see here, 4 LEDs, in this case in different colors. It doesn't have to be exactly a bar graph. And these are the 4 deep switches where you transfer here your data, your bits. And this is a PIC micro where you can see this is power, this is ground, and the 4 bits, these 4 bits are connected to here, RB4 through RB7. And RC0, you can see here the bits for these connections to the LEDs. These red cables are just for power. Okay, they are repeated because in this PC board we need to supply power to both sides. Okay, so let's start with the code. And in this case, I'm gonna start right here. This is the heart of the code, so I'm going to mark this with yellow color. So the first thing we do is we clear the 3 ports, and that way we make sure there is no data. This is a label called RPT. Okay, we notice that you have the column to identify it as a label. We place here a pause of 200 milliseconds to wait after clearing the ports. This is variable. You can make, you can include these pauses at any time in the beginning of the code. I do it especially because when you turn on the power supply, I wait these milliseconds to have the power supply, the voltage stable. Now we transferred the contents of port B are now transferred to variable N, okay? And that's the way to read port B in this software. And then we have this N, which is a variable, and we have to shift the contents 4 positions to the left. So RB4, so that RB4 to RB7 correspond to RC0 through RC3. So we shift these 4 positions and in this variable, and now we store the after the shift is made, it is stored in this variable called result. Okay, then we transfer variable result to port C, and we can turn on one LED or on port A, that one, for 200 milliseconds. okay, to indicate the user that the data is ready. Okay, so on LAB1 we are putting an LED. So for 200 milliseconds it is on, and then we go to this label. After the 200 milliseconds we go to this label again, and it keeps repeating, so it keeps reading the port. It keeps, in this case, clearing, and then another pause, and then reading, okay, so that you can see a new result. So you can move the switches, and then you will see how the data changes, because it is updating, we can say, every 200 milliseconds. So you change these bits, you will see the changes here after 200 milliseconds. Okay, and of course 200 milliseconds here, and then 200 milliseconds. So after 400 milliseconds we add them. Okay, so this is the code, and where first we send master clear to voltage internally. Master clear is one of the pins to clear the micro. So if we don't use it, which is called RA3, if we don't use it, we can use RA3 for another functions, and with this instruction we send internally the master clear function to voltage. So we rest assured that the microcontroller will be cleared when starting the code. Okay. Now we have here the instruction. Let me clarify this image a little bit. Okay, and now we have here this instruction, answer A, where first we make it equal to 0. So port A is all digital. By default it's all equal to 1s, but we have to make it equal to 0s. In this case 6 zeros, because we have 6 bits on port A. Then we make port A, we set it, or we configure it as an input with this instruction. Then because I'm transferring the 6 bits into trace A, so all those bits are equal to 1, and port A will be an input. So now I clear the latches on port A, then the answer B equal to 0. That way I'm making port B equal to digital. You can put that comment there. And also we can, now I'm doing trace B equal to these 4 ones, making RB4 through RB7 as an input. Okay, and I know these ones must be here. Let me make this correction. I'm sorry for this. Okay, right there. Okay, so I know these bits do not exist on port B, but I'm setting RB4 through RB7 equals to 1, so I'm making those inputs, those 4 channels inputs. Then I clear a latch B, because we don't use it, and the uncell C, I'm clearing port C to make it all digital. Okay, I'm not using latch C, so I'm clearing latch C, and try C is equal to 0 to notice that port C now is set as an output. In these other cases, the trace A, trace B were inputs, but now only port C will be an output. So we have here the variable byte n. So I'm declaring this variable as a byte, variable n. Okay, variable n, and you may get another color. So variable n is a variable byte. Okay, now we have here the result variable byte. So we are declaring another variable in this case called result. The first one I'm declaring is N, the other I'm declaring is result. If you don't declare them, the software will give you an error, because the software allocates memory to these two variables, and those are RAM memory locations. Now we clear OSTune and OSCON. OSTune is clear and OSCON is equal to 6A, hexadecimal, $sign means hexadecimal, so that we can set the internal oscillator to 4 megahertz, which is the standard frequency. That most of the times we're working at that frequency. And the option reg.7 is used to connect all the resistors on port, on any port to enable those resistors. So I'm using WP UB equal to 0. So in such a way that those resistors are enabled. Okay, the resistors on ports are or lines RB4 through RB7. Okay, the resistors on port C are not used. That's why these are all equal to 0. Now, this is the heart of the code that I was explaining a moment ago. So we clear again, or we clear here the 3 ports. So we wait 200 milliseconds. Then we transfer the contents to variable N. We shift the contents for positions to the left. And now the data bits are in the correct position. So I have here the port C, the result transferred to port C. I turn on this LED on RA1 and wait another 200 milliseconds and go to repeat. So the software keeps repeating this instruction again and again. Okay, so this is how this software works. And of course I can test it. Let me remove all the highlights that I was putting here. So I'm gonna place here. Okay, so I'm gonna leave them this way. Okay, so this is the explanation for that code. And what we can do next is to compile this code. So what I'm doing, I'm copying and pasting all this code to the software. So let me go to the microcode software, and right here I have the microcode software. So you can see here I made a copy paste of the instructions, and so you can every time, as I said before, every time you see this green letters, and these are comments to the text. Okay, so notice right here that try say it might be separated, but it doesn't matter, it will not create an error, so you can have it in that way. So now we are ready, because I transfer all this code, and you see it is ready. So you have to add the end command to end this software. And I'm not using the ASM instruction and end ASM because this is PVP3 code. So to make sure that this software is working good, I'm going to show you here the that I have to save this code. Then I'm going to compile it right here on the upper left corner. I already selected the PIC 16F1619, and you can see there the software has been successfully compiled with 90 words used right here, 90 words used of the 8,000 kilobytes of memory that I have available. So the code is ready, and if you go to the lab, you will have to use this one, compile, program, and the code will be transferred using a programmer. And that way you can test it and you can make changes to this code. And there are many things that you can do. For example, if you want to transfer, instead of transferring your code to or reading your code from RB, port RB, and you want to transfer the code to, let's say you are reading port B, and you want to transfer to port C. So to the other positions, and when I say other positions, I'm saying, notice that I'm making this instruction, the shift, the 4 shifts to the left. I am putting a semicolon here to make it a comment. So it's like this instruction is not working, only the ones in black and blue. So what I'm doing, I'm reading port B, RB4 through RB7. I'm storing that in this location. And then I'm transferring I need to transfer the result. The result is now in variable n. So I can transfer, instead of putting here result, I'm going to put here n. You see? So I'm transferring now n to port C. So what is going to happen is that the positions, the RB4 through RB7 will be transferred to RC4 through RC7. Okay, instead of using instead of shifting those to RC0 through RC3. Okay, that's one way to do it. Okay, now let's say you want to read port A and transfer port A to port C. So if you transfer port A to port C is also an output. But if we have, because right here we were reading port B. So if we want to read port A, notice that right here port A is an input. It's a digital input. So that's not a problem. So I'm going to put here port A. Because I want to read port A, transfer it to variable n, and then I want to transfer the contents, the 6 bits on port A. I want to transfer those to, I said port C. So this is the way to do it. Okay. In this case, I'm transferring all the 6 bits on port A, which is RA0 through RA5, so 6 bits, and they are transferred to RC0 through RC5. Okay, and then I want to place an LED on port B dot 4. Right there. Well, let's say port B dot 7. Right there. And I will turn on this LED. Okay. So port A is an input, port C is an output. Port B dot 7 must be an output because I want to turn on the LED right there. So port B7 must be an output. So if I want to make all the contents on port B, I want to make them outputs. So this is the way to do it. I can write all zeros or just 1 0, decimal 0. So that will make all port B an output. So let me put here this comment. Port B output. Okay, configure as an output. And that way the LED connected here will be configured to turn on for 200 milliseconds. Okay, and then because it goes here, because it goes back here to RPT, then what is going to happen is that the LED will be off. Okay, because I'm right here, I'm clearing port B. Okay, for 200 milliseconds. Then I'm reading again port A to variable n, then variable n to port C. So I'm transferring the data from port A to port C. Okay, and port A is already an input because I have it configured right there. in this instruction, okay? And it is digital right here. Uncell means that port A is digital. Okay, so this is all for today. I was here just explaining one of the first practices that we are doing. And so you can, of course, in any change that I was explaining here, for example, you want to hold the data for 1 second, you have to write there 1000. Okay, if you want to turn on the LED for 1 second, and you want to reduce this to 1 millisecond, this first one, you just say that. So after clearing ports, wait 1 millisecond, transfer the contents to from port A to N to port C, then turn on this LED on RB7, wait 1 second, and after 1 second, go to repeat. Okay, so you will have 1001 milliseconds right here, but the LED will be on for 1 second, and the data will be cleared on port C. So the data on port C, this data right there, will be there. Data will be held for how long? 1000 milliseconds, which is 1.00 seconds. Okay, so these are just changes that you can do. You can compile it and test it with a real micro. So going back to the code, every time you make changes and you want to connect an LED on RB7, or you have to make changes in the hardware. If you are making changes in the software, right here, you have to make changes in the hardware. Okay, that's all for today. Thank you.